Hello everyone. Let's start next chapter. Next chapter is chapter 9, chemical bond, and in this chapter we will explore the forces that hold matters together, called the chemical bond. Let's start with revisiting what is a chemical compound. A chemical compound is a pure substance formed when two or more elements chemically combine. And a key characteristic of a compound is that compounds have different properties from the elements that form the compound. For instance, if we look at water has properties uh, completely different from the very flammable hydrogen gas and the life-sustaining oxygen gas. Or in other words, if we combined these two atoms of hydrogen with one atom of oxygen, this gaseous element will create a new substance called water, which is in liquid form. And we know water has a completely different characteristic compared to hydrogen and oxygen by themselves. And the atoms in a compound are held together. These atoms in any compound are held together by chemical bonds. The chemical bond is an attractive force and that holds this element together uh, to form a substance, and the the chemical bond is what determines the compound's structure as well as properties. And if we look at here, anything above this line, we have the same elements combining together to form a stable molecule, and that these are not compound, rather they are diatomic molecules. And we have, if you look at here, different elements combining together to form compound. And closely related to this chemical bonds are chemical reaction. Uh, a chemical reaction is a process where one or more substances are transformed into new substances by rearranging their arranging their atoms. And this process of chemical reaction involves the formation or breaking of chemical bonds, and the substances or the matter that takes part in a chemical reaction is called reactant, and the matter we will get after the reaction are called product. So basically, the new molecules formed are called product, and the old ones are called reactants. And we should also note that any chemical reactions involve change in energy, and this change in energy can be either chemical reaction will absorb energy or it will release energy. And based on whether the chemical reaction will absorb or release energy, we can classify a chemical reaction into two categories, namely endothermic reaction, where the reaction will absorb energy, and exothermic reaction, where the reaction will release energy. The for example of exothermic reaction, we can see we we can see an example of lighting a match where when we light the match, it will release both heat and light energy, and as the reaction resulted in a release of heat, we call the reaction exothermic reaction. I don't see example written here, but and a common example of endothermic reaction is ice melting. So solid ice, if we add heat energy in a solid ice, it will result in water in liquid form. So if we look at here, this process absorbed heat, so we call it endothermic reaction. And the chemical changes the chemical changes in chemical reaction is irreversible uh, typically irreversible by simple physical means. For example, if we look at in diagram, if you burn wood to ash, the ash cannot be turned back into wood, and we can turn this charcoal or ash back to wood. So the chemical reaction are typically irreversible by simple physical means. And in order to represent these chemical reactions, we use a system, a symbolic summary called chemical equation. And this chemical equation is a symbolic summary that shows uh, the reactants and product of a chemical reaction. And before we move further on chemical bond, first we need to define valence electron and ions. We talked about this a little bit in previous chapter. Let's go through it again. The the ability of an atom to form bonds is related to electrons, specifically the valence electron. And the valence electron is defined as the electrons in the outermost cells. Valence electrons are the electrons present in the outermost cell of an atom, and this valence electron is what determines the chemical reactivity, chemical property, and the chemical reactivity of any atom. And the driving force that behind this bonding of any atom is the octet rule. And this octet rule states that uh, atoms will try to be in a more stable configuration by fulfilling this outermost shell. And typically this outermost shell is stable when there are 8 valence electrons. And in order for these atoms to gain to be stable configuration, atoms tend to either gain, lose, or share electrons, and share electrons to form a stable configuration. And now we know what's a valence electron, and let's have a look at valency, sometimes also called valence. Instead of valency, you will also see it written as just as valence. And valency is the number of electrons an atom must either gain or lose or share to reach a stable configuration. And when we are talking about stable configuration, generally uh, stable configuration involves 8 electrons in the atom's outermost shell. And let's look at an example here. Oxygen is the atomic number is 8, so we know there are 8 electrons in an oxygen atoms, and if we draw this electronic configuration, the first energy level will have 2 electrons, and the second energy level will have there are 8, since there are 2 already here, we have 6 electrons left. And in order for this oxygen atoms to be stable, it will require 2 more electrons to be in the stable configuration. So the valency of oxygen atom is 2. Similarly, if we look at sodium, the atomic number is 11, number of neutron is 12, and if we draw this electronic configuration, first energy level have 2 electrons, second energy level have 8 electrons and 1 left, which will be in the third energy level. And now if we look at this configuration, we can say the valence electron is 1, and in order for this sodium atom to be stable, it will lose this 1 electron. So we call the valency of sodium is 1. And we can also write whether it's positive or negative. In the first example of oxygen, we can see here it will require to add to gain 2 more electrons, and it will lose 1. So this will be, there will be more negative charges compared to a number of positive charges. So this is 2 negative, 2 minus, and this will be 1 plus. And we can easily determine this number of valence electron for main groups using a periodic table. Main elements from the main group using periodic table. And if we look at here, there are some examples from group 1 to 2. All the elements in group 1 and 2 have 2 valence. 1 and 2 group 1 and 2 will have 1 and 2 valence electron. Group 1 will have 1 valence electron, group 2 will have 2 valence electron. We can see here. And then from group 13 to group 18, in order to calculate the valence electron, you take the group number and subtract 10. So this is group 10, group 13, and group 13 minus 10 is 3. So we have 3 valence electron. For group 14, 14 minus 10 is 4, 4 valence electron. Group 15, 15 minus 10, 5 valence electron, and so on. And one thing to keep note is that the rule this rule of valence electron does not apply to helium and transition metal. For example, here we can see the valence electron is only 2 for helium when it's in group 18. And in order to represent this valence electron, we generally use electron dot diagram, also called Lewis diagram. And this electron dot or Lewis diagram is a simple way to represent valence electron, and this diagram shows only the valence electron as dots around the elemental symbol. Here we can see in this diagram helium sorry hydrogen, the first element, group 1, has one valence electron, so we have one dot. And then group 13 has three valence electron. Sorry, let's look at 2 as well. So group 2 has 2 electrons, so we can see here 2 dots around the symbol. Group 3 has 3 valence electrons, so we will see 3 dots around the element. Group 4 has 4 valence electron, and if you see here there are 4 dots around the number. Group 5 has a 5 valence electron. Sorry, group 14. Group 15 has 5 valence electron. Group 16 has 6 valence electron. Group 17 has 7 valence electron, and group 18 has 8 valence electron. And there is a systematic way to create this electron diagram, and these steps are mentioned here. We will begin with for example, let's look at a nitrogen. Nitrogen is here, group 15. So group 15, that means we have 15 minus 10 equals to 5 valence electron. So we will begin with elements symbol, and then we will determine the valence electron. We just did that using group number, and then we will place 2 dots per side for a total of up to 8 electrons. But before doing that, first we have to place 1 dot on each side, 1 2 3 4, and then once we have 4 dots, we will start pairing the single bond into two electrons. Similarly, if we look at oxygen, first we will have so oxygen has 6 valence electrons, so we start with 1 dot on each side and then start pairing in anti-clockwise direction. So here now we have 1 2 3 4 5 6 6 electrons. So this is the Lewis diagram for oxygen atom. And in this Lewis diagram, this single dot are unpaired electrons, meaning these electrons can form a covalent bond with the other atom, while this paired dots represent lone pairs, and they typically do not form bonds with other material. Now let's look at a chemical bond. A chemical bond is the attractive force that holds atom together in both compounds or molecules, allowing them to form more stable electronic configuration. When we say more stable, generally we are talking about 8 electrons in their outermost shell. And there are two type of chemical bonds. First, ionic bond and covalent bond. Ionic bond is created by transfer. Ionic bond is created when electron transfer from one atom to another atom, and the covalent bond is formed when electrons are shared by two atoms, and the the chemical bond in an ionic bond is mainly because of electrostatic attraction between two ions, and when this ionic reaction happens, this electrostatic attraction is between positive cations and negative anion. And for covalent bond, the when sharing two electrons, uh, the the attraction between this chemical bond sorry between these atoms is because of the shared electron between two atoms. And in general, the ionic bond is formed between metal and non-metal, and covalent bond is formed between uh, two non-metallic elements. And with that, let's look at in more detail for ionic bond. As we said, the ionic bond is characterized by a transfer of electrons from one atom to another, resulting in the formation of ions. And like we said before, the positively charged ion are called cation, and negatively charged ion are called anion. And the binding force between these atoms is the electrostatic attraction between these two forces, and the ionic bond, the chemical created by this ionic bond, the ionic compounds are very stable, and very stable, and these structures, this ionic compound are generally crystalline solid, which means this material, these compounds have orderly geometric structure. And for example of ionic bond, we can see sodium fluoride, sodium chloride, and like we said, this ionic bond is formed between a metal and non-metal when these atoms from group 1 loses electrons. Sorry, group 1 will lose 1 electron, group 2 will lose 2 electron to non-metal materials from either group 17 or 16, which will gain either 1 or 2 electrons to form an ionic bond. Let's look at here in example. There is a sodium atom, fluorine atom, and this sodium will lose one electron to fluorine to form a stable electronic configuration, creating overall neutral sodium fluoride. And we can also see here well-defined crystal structure of sodium chloride. As we mentioned before, this ionic bond form a orderly geometric structure we also call crystal structures. And there is a standard way of naming ionic compounds, and we will start with writing the name of cation first. For example, if we look at the reaction between sodium and chlorine, we will start with sodium, because as we see from the previous slide, when reacting, sodium will lose one electron, making a net positive charge when forming an ion. So we know sodium will form a cation, and like we said, when we are naming a ionic compound, we will start with symbol and charge of the cation. So we have sodium and the anion in the second, and then chlorine, and then take the name of negative non-metal element and give it ide. So we know this is chlorine, so we will change its name to ide form, so chloride. So from chlorine we will make it chloride, and now we will combine these two to create a name of this chemical. So the first element was sodium and the second element was chlorine, and we changed the name with IDE ending, so the final name is sodium chloride. So this is a standard way of naming an ionic compound, and in order to write the chemical formula for ionic bond, you can use the crisscross method. Let's look at the crisscross method here. So we know that the valency of sodium is 1 and the valency of chlorine is also 1. So the crisscross method is basically, we will assign this valency to the other atom. So if you look at here, sodium, and if we assign this the valency of other material to sodium, we have sodium 1 and chlorine 1. Since this 1 is already implied, can be implied within this symbol, so we don't write 1, so we basically write sodium chloride as NaCl instead of Na1Cl1. And if we were to look another example here, we can look at here. We have barium. Ba is barium, I is iodine, and if we want to use this crisscross method of writing the chemical formula, for example, if we were to write chemical formula of barium iodide here, the valency, if you go back to the periodic table, you can find that the valency of barium is 2 and the valency of iodine is 1. Now if we crisscross them, we'll assign barium with 1 and iodine with 2. Since 1 is implied without writing it, so the chemical formula will be Ba2. And in order to name it, we know we will first call the name of the first element, and we know Ba is barium and I is iodine. Barium and iodine. Now if we convert this iodine with IDE form, we will get barium iodide. Here, these are the most common material that form ionic bond. We can see here all the elements in group 1 and group 2 has a positive valency, and they combine with non-metals in group 16 or 17 which has a negative valency, and we just saw how they combined with each other to form ionic bond. Now let's look at covalent bond. A covalent bond is formed by sharing of a valence electron rather than transfer between two electrons. We can see in example here we have atom 1, atom 2, and then if you look at this valence electrons, this outer shell valence electron, here we have 2, 4, 6 and 7, 2, 4, 6 and 7, and in order to achieve stable outer configuration for both atom, and they will require one more electron. So instead of transferring from one to other and making unstable structure, they will share one electrons between them, forming a covalent bond with a stable outermost cell configuration. And one key characteristic of this covalent bond is that the compound created by covalent bond are generally electrically neutral, and the force that creates this covalent bond is because of this overlap of these electron clouds, creating a net attractive force because of this overlap between their orbital cloud. And there are mainly the covalent bond can be divided into multiple categories. For example, single covalent bond, double covalent bond, or there can also be triple covalent bond. And as the name suggests, a single covalent bond has one pair or two electrons from one from each atom uh, shared between two atoms, and double covalent bond will have two pair of electrons or four electrons shared between two electrons. And if it's a triple covalent bond, you will have three pair of electrons. And one way to show this covalent bond is using this symbol here. We can see in the left there is a Lewis structure, and in the right we are using this structural diagram, and this each line here shows one bond. So one hydrogen, one atom of hydrogen will create one bond, one covalent bond with another hydrogen to form a stable structure. Similarly, if you look at here, one oxygen atom will have two bond with other oxygen atom to form a stable configuration. If we look at nitrogen will have three bond between two nitrogen atoms to form a stable outer must configuration. And with that, this covalent bonds will have bond polarity, and bond polarity refers to this unequal sharing of electrons. So bond polarity is defined by unequal sharing of electrons in a covalent bond, and this unequal sharing of unequal sharing of electrons is due to a difference in electronegativity between electronegativity between the bonded atoms. And if you remember from previous video, the electronegativity is a measure of an atom's ability to attract electrons, or in other words we can say it's an atom's ability to attract uh, shared electrons in a chemical bond. And this electronegativity can be found from generally from periodic table with electronegativity. And as we say, bond polarity is a result of unequal sharing of electrons, and there are this polarity can be based on this polarity, covalent bond can be divided into two categories, mainly two categories. First, a polar bond and a non-polar bond. A polar bond occurs when there is a significant difference in electronegativity. mm, Significant difference in electronegativity. Typically, if the electronegativity and the difference in electronegativity between two elements is between 0.1 and 0.2, the covalent bond formed will be a polar bond. And this difference in electronegativity is generally represented by this delta symbol, and it can either be partially negative represented by delta minus, and partially positive represented by delta plus charges. An example we can see here, the an example of polar bond is hydrochloride, HCl. And if we look at here, chlorine is more electronegative than hydrogen. And if we go back to a periodic table and find the electronegativity value for hydrogen and chlorine, and if you subtract the electronegativity between hydrogen and chlorine, you will find that the electronegativity will be, the difference in electronegativity will be between somewhere between 0.1 and 0.2, resulting in a polar bond. And for a non-polar bond occurs when electrons are shared equally, because the atom have similar or identical electronegativities, meaning change the difference in electronegativity between two electrons, two atoms are uh, the difference in electronegativity between two atoms is 0. So an example, the electronegativity of two hydrogen atoms combining together will be 0, two oxygen element combining together will be 0. So the molecule like H2O2 are formed because of a non-polar bond, have a non-polar bond because their electronegativity uh, are the same, resulting in zero difference. And in order to here's some more definition of a polar covalent bond and a non-polar covalent bond. Like we said, polar covalent bond has electronegativity difference between two combining electrons, that's in between 0.1 and 0.2. Example, water is a polar covalent bond, HCl, NH3, etc. Similarly, we have non-polar covalent bonds, H2O2 and 2, etc. And it's also clear from this diagram here. For polar bond, we can see here water sharing bond here to form a covalent bond, and the overall result in electronegativity, if we calculate the difference in electronegativity between two atoms of hydrogen and one atom of oxygen, the difference will be in between 0.1 and 0.2, resulting in a polar bond. And like we said before, the electronegativity of the elements can be found from the periodic table, and we can see here. Let's look at one of the example, HCl. So the electronegativity periodic table. Now look at the example we just gave before, HCl. Now if we look at the electronegativity of hydrogen, we can find that the electronegativity of hydrogen is 2.2 and the electronegativity of chlorine is 3.16. And if we calculate the difference between the electronegativity of these two elements, we'll get 1.6 minus 2.2, which is around 0.96. And if we go back to our previous slide, we know the covalent bond between this element will be polar if the difference between their electronegativity is between 0.1 to 0.1 to 2, and the answer is 0.96, which is in between 0.1 to 2. So we can say this is a polar covalent bond. And in order to name a covalent bond, bond, there are also few rules. The first, name the first element in the formula using a prefix to show the number of atoms, and we generally omit the first prefix mono if there's only one element. And then after naming the first element, we will name the second element using appropriate prefix and changing the ending of the element's name with "id," similar to the first one. So for example, if we look at here, following this naming convention, so first we will start with the first one, right? And the element name is carbon. And if we look at here, there's only one carbon, so this is mono. And we can see here all these Greek letters: mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, and so on. So the first element is carbon, and then there's only one carbon, so the prefix is mono. And then second is oxygen, and we have one oxygen, this is also mono, and we combine these two, we will get carbon mono, and oxygen should be converted to oxide, IDE, so carbon monoxide. Similarly, let's look at this CO2. CO2, again there's only one carbon, which is mono, so as we said, we will omit mono because it's implied. If we don't need to call it mono, it's implied. And if you look at here, there are two oxygen atoms, so this is carbon, and then there are two oxygens, so carbon di, and this is oxygen, we'll convert it into ide, so carbon dioxide. So CO2 is carbon dioxide, CO is carbon monoxide. Similarly, if we look at here, we have 2 nitrogen and 5 oxygen, so nitrogen, and if we look at here, 2 is di, so dinitrogen, and 5 is penta oxide, so N2O5 is called dinitrogen pentaoxide. This is how we will name covalent compounds. And in order to write covalence bond, the valency of an atom is what dictates how many covalent bond it can form. And the valency of these electrons, these atoms: oxygen have 2, nitrogen has 3, carbon has 4, and so on. And whenever we are writing the formula, we will we will start with the name first. The name is here, and as we see, this is carbon, and di is 2, and oxygen O2. Similarly, carbon tetrachloride, so carbon tetra is 4, carbon tetrachloride. And this covalent compound can also be written as these structures. And if we look at here, we just said this each line shows a bond, and here we can see this structure can be written like this: 1 carbon and 2 oxygen, 1 carbon, 4 chlorine, and hydrogen can only have one bond, so one valence. Oxygen has s- six electrons in the valence, and like we said, all these paired electrons do not take part in this bond formation. So we can have two bonds, and this two bond can be with a single atom or two different atoms like this. It can create a bond with the two different atoms or one single atom. Similarly, if we look at nitrogen, nitrogen has three valence electrons, so it can either combine with three different atoms or two different atoms with one single pair with one atoms and double pair with another atom, or it can combine with an atom with three three bonds. Similarly, carbon has four valence, so it can form a structure with four different atoms or three different atoms, two different atoms, or uh, two different atoms with a double bond, or two different atoms with single bond and triple bonds. Now we know how to form the covalent, how to name these bonds, or the chemical formulas for different elements. Let's look at why it is called H2O rather than uh, OH2. So if you look at here, it looks like the same structure, right? This is two atoms of hydrogen and one atom of oxygen, one atom of oxygen, two atoms of hydrogen. But we don't write it this way. We always write the chemical formula for water as H2O, and we want to know why it is. Right. As we saw before here, if we look at oxygen, oxygen can form two bonds because it has two valency, but hydrogen can form only one bond because it has one valency. So if we look at this equation, this chemical formula H2O, oxygen is the central atom because we want a reaction that will have two hydrogen atoms. So hydrogen can have only one bond. So the central atom should be oxygen because oxygen can bond with two hydrogen, while hydrogen can only form one bond, so it cannot be the uh, central atom. And the way H2O and OH is written is also related to the electronegativity. And as we say, when we write OH2, it suggests that hydrogen is the central atom rather than oxygen, which is incorrect way of writing it. But if we are writing something like an ion form, for example here hydroxide, if you look at here, this is an ion, right? So it has a charge of -1, so oxygen and hydrogen has the same level of bonding because it is still can have form one bond. From here, because it has a negative charge, it can be written as OH, but water cannot be written as OH2 because it gives a sense that hydrogen is forming two bond with oxygen, which is not a correct way. And the naming convention are generally the naming convention in chemical structure is generally following this IUPAC naming convention. And if you see here, hydrogen atoms are listed first when bonded to more electronegative elements only if they are central. So if the relation where hydrogen is center, then it will be written as this form. Otherwise, hydrogen will be listed first when bonded to more electronegative elements. And as we know, if we remember, the periodic table electronegativity increases as you go from left to right in a periodic table, and hydrogen is somewhere here, oxygen is somewhere here. So oxygen has more electronegativity, and if we follow this logic from higher electronegativity, we have to write hydrogen first. So we will get H2O instead of OH2.